Yes.
Okay. Okay. And next speaker is how to pronounce.
Vjosa. Blakaj.
Blakaj. That this is the joint talk is Michael Wolf. The title is Transcendental property of entropy constraint set. So please start.
Thank you. Thank you for the introduction, and thank you, the organizers, for setting up this event. So today I will be talking about a joint work that me and my supervisor, Michael Wolf, have done in transcendental properties of entropy constraint sets. So as a first thing that I want to do here is I want to explain the first word that we have on the title, transcendental. I assume all of us have heard in the past about algebraic numbers, which are basically numbers that are roots of polynomials with integer coefficients. And every number which is not a solution of such a polynomial is said to be transcendental. So such separation, algebraic versus transcendental, not only exists for numbers, but exists also for functions and for sets. And this is basically a tool that we use in our work. And we will call a function algebraic if its graph is basically the solution of some polynomial. And every function which is not a solution of such polynomial then will be called transcendental. And the usual suspects for these functions are usually the exponential and the logarithm, and many other functions. And regarding sets, here comes the word semi-algebraic. So a subset of some real vector space will be called semi-algebraic if can be written as a finite union of polynomial inequalities, basically. So the word semi here is just about the fact that we are using inequalities now here, except equalities, basically. So any set that cannot be written like this is called, again, transcendental. Something else that we will use on this work, and I'll talk about it, are the so-called Nash manifolds and Nash maps. And Nash manifolds are basically just manifolds that are at once smooth and semi-algebraic. And why do I use them here? Is because I can basically write every semi-algebraic set as a disjoint union of finitely many of Nash manifolds. And Nash maps are defined similarly. They're just maps who are smooth and algebraic basically at the same time. So why do we care about these things, or how are these related to quantum information theory? So basically, this separation between transcendental and semi-algebraic often comes hand in hand with separation between single shot settings and asymptotic settings, or finite theories and infinite theories, basically. So this is the idea behind why we wanted to make use of this in our work also. Before I dive more into our work, I want to talk about the motivation which led us work into these specific sets. So there's catalytic state transformations, which were basically worked by Willing and co-authors in 2019. So what are these transformations? So for a given density operator rho prime, I want to transfer this, transform into rho, which is the target state. And I can do this under the following rules. So I can add basically an ancilla state to my initial state, and I can apply a global unitary to my combined state, basically, rho prime tensor sigma. And my final state, which might be correlated, so rho 1, 2 is such that basically in one subsystem, I get the target state, or I get something which is approximately very close basically to my target state. So I denote this by rho 1. And in my other subsystem, I get back sigma, so basically the ancilla state. And this is used basically as a catalyst because it's helping me to perform a transformation, and I get it untouched in the end, which means I can use it for further transformations. So when are these transformations possible? Basically, given rho prime, what is the state of reachable, what is the set, sorry, of the reachable states rho prime, rho, sorry, again. So basically for a given rho prime, I define Sn as the set of reachable states under the constraint that I can use a catalyst of a maximum dimension n. So basically here I just wrote the conditions that I talked previously. And this is just a subset of density operators, basically. And another subset that I will introduce is the set S, which is basically the set of all states that have a bigger von Neumann entropy than the initial state rho prime. We all know the definition of the von Neumann entropy, but I just wrote it here because I'm using the logarithm with the base E. And later on, I will explain that this in the end won't matter, basically the base that I'm using. So there is another observation, which was done by Wilming a year later after the first paper, which basically said that if I take the union over of all these Sn sets over n, in the end, I will get the set S, which is basically the set of states which have higher von Neumann entropy than my initial state. So this, in some sense, is the limit when I take n to infinity, which means I don't have any constraints, basically, on my catalyst. And a question which one might ask themselves is whether there exists basically a finite n, which would depend somehow on the dimension of your system, such that these two sets are the same. So maybe we don't have to use an infinite dimensional catalyst. Maybe there is a finite dimensional catalyst that does the job, basically. And how we attach this question is basically the separation between semi-algebraic and transcendental world. And the first observation that we make is basically that the set Sn is semi-algebraic because everything that is defined in the set basically can be written as a polynomial equality or inequality, or a finite union of those. And also here, the fact that we have quantifiers is not a problem, and this is because of a very strong theorem in algebraic geometry, which is known by Vjosa, basically, and says that if you already have a semi-algebraic set, then using quantifiers won't make you leave this world. So you're basically still semi-algebraic. And the other set is the one which was more difficult. And basically, this is a set which has the logarithm on it. And earlier I mentioned that the logarithm is a transcendental function. So basically, this smells like a transcendental set. And if this is the case, then we can clearly see that basically these two sets are not the same. So Sn for a finite n is not equal with S, basically. So the question is, are these sets basically transcendental or not? And in order to answer this question, we came up with a criteria which basically discriminates between semi-algebraic and non-semi-algebraic sets. So basically, the theorem says that if you're coming from an algebraic world, the main two observations here are that basically, analytic continuation of algebraic functions have at most a finite number of branches, or in particular, a compact Riemann surface. And also, if a set is given as a level set of some differentiable function, then the normal space, of this set is particularly easy, basically, to be accessed. And what we do is, in order to answer the previous question, we use the second part of this theorem and try to use the fact that the logarithmic function has an infinite number of branches. Okay, so this is still not yet everything we need to answer this question. So we have to be careful when we consider basically dimensions, because for dimension 2, basically the set of density operators that have fixed von Neumann entropy can be written as the set of states by checking their purity, basically. So this is for qubits, and for qubits, we know that in the block representation, this is just a sphere, and a sphere is very algebraic. So basically, the answer to whether entropy constrained sets are transcendental in dimensions 2, this is negative, because in these dimensions, then these sets are still algebraic or semi-algebraic, basically. When we go on higher dimensions, then things change, basically. And the answer here is yes. And I will try to present the proof idea by some pictures put in together. So basically, if this one here is the set of states that have fixed entropy, then, okay, this is a manifold. Then I'm applying this map here, which is basically an algebraic diffeomorphism, because I am assuming initially that this manifold here is algebraic. So I'm not changing anything. I'm just parameterizing it into another manifold such that the first d-1 components here are basically the eigenvalues of the operator that I'm considering. What I do next is I take a point basically in my manifold and I consider the normal vector. So this is just the vector which is perpendicular to the tangent space at that specific point. And I can assume that this normal vector has norm 1, so basically is a unit vector. And I can do such assignments to every point on my manifold, basically. So this assignment in some parts of mathematics is known as the Gauss map. And the next thing that I do is I take a path. So this orange curve here, I take a path in my manifold that goes through my point X. And how do I get such a path? So what I do is I intersect an algebraic surface with my manifold in order to get such a path. And I can do the same. Basically, I can just map it to the unit sphere via the Gauss map similarly. Next, what I do is I consider any of the components of my normal vectors here such that they're not constant on my path. And this will give me rise to a function from R to R, basically. And what I do further on is I take this function and I put it in the complex plane. And a technique which is used in complex analysis is analytic continuation. So basically to expand the domain of my function. And when I take the analytic continuation of such function, then I end up with an infinite number of branches. So basically, we all know that when we consider the logarithmic function, this always gives rise to an infinite number of branches or a non-compact Riemann surface, which contradicts my assumption, because if everything was algebraic or semi-algebraic, then these branches would have ended at some point, because algebraic functions have at most a finite number of branches, basically. And this is exactly how the fact that the logarithm is in the definition of the von Neumann entropy gives rise to the transcendental nature of the level sets of the von Neumann entropy. So what did we exactly prove? So we showed that for dimensions greater than 2 and for the entropy values not being extremal, the set of density operators with fixed von Neumann entropy is nowhere semi-algebraic or is everywhere transcendental. So we work locally basically here by always intersecting with an open set in the space of Hermitian D by D matrices. And since we had this result, we thought, okay, what would happen if we would add more constraints basically to such a set, not only having a fixed von Neumann entropy, but some other constraints. And this is what I'll show. Oh, okay, sorry, before I go there, I just mentioned 2 remarks. So basically this statement here in 2 will hold true for any base of the logarithm, because if I change the base of the logarithm here, that means that I'm just changing the value of C. And also the same result will hold true for if I use, instead of equality here, any of the following inequalities, because from semi-algebraic geometry, then the boundary of a semi-algebraic set still remains semi-algebraic, basically. Okay, so now going back to the additional constraints to the level set of the entropy. So these constraints could be anything from the distance of the state to a specific target, the energy of the state, or the expectation value of any observable, basically. And how do I express these mathematically? So these are described using a differentiable function from the set of D by D positive definite matrices to R. And basically the theorem is quite similar, with the only difference that I'm adding this differentiable function. And I assume also to have a fixed value, basically. And another constraint that we add is that the commutator between rho and the gradient of the function at rho is different from 0. And we do so because we don't want that this is depending entirely on the spectrum of rho. And again, by just using the same proof idea, more or less, that I presented before, we can show that this set is again not semi-algebraic in any neighborhood of the state rho, basically. And as an immediate application of this theorem was basically studying whether the level sets of the quantum relative entropy are semi-algebraic or not. And since basically relative entropy contains in its definition the von Neumann entropy, and this is basically the H function that I talked about earlier. So basically here I consider any positive definite density matrix sigma. So somehow I'm fixing an arbitrary sigma here and I'm varying over rho. So I fulfill the conditions of my previous theorem. And again, when I intersect in an open subset of the Hermitian D by D matrices, again, following again the same proof idea as before, and using the fact that I can split basically this set R into the intersection of two sets. So one basically being the level set of the entropy and the other as a pre-image of trace or my H function. So I have to be careful here a bit whether the intersection is still a manifold. And similarly, so just extending the proof, we show again that these sets are not semi-algebraic unless the set itself is empty. As a takeaway of this talk, what I wanted to say is basically, oh, was there a question? Sorry.
Okay, please. No problem.
Okay. So basically, the set of reachable states with a finite dimensional catalyst, so with a catalyst at most n, is never equal with the set of density operators that have greater von Neumann entropy than the initial state. So these two initial states that I defined S and Sn are not the same. So basically, there's no universal bound of the dimension of the catalyst that you need to make such transitions. And as a message to take away is that this distinction between single shot asymptotic and finite theories and infinite theories comes often hand in hand with this separation between having something semi-algebraic or having something transcendental. And sometimes we can use these separations so for no-go results. So basically that single shot characterization of information theoretic quantities as the one that as catalytic transformation, which was basically that entropies can characterize such transitions only if we consider infinite ancillary systems, basically. And we strongly believe that the variance that of the presented arguments here will also apply to many other entropy quantities that appear in classical and quantum information theory. From the proof that I showed earlier, then the level sets, when we consider the von Neumann entropy, are not transcendental. From the proof, you can also see that the same result basically holds true in case you use the classical version. So we're using the Shannon entropy and not the von Neumann entropy. But we believe that also with other entropy measures, we can prove similar results. And with this, basically, this is the end of my talk. And I thank you for your attention, and questions are welcome.
Thank you for a nice talk. Is there any question or comment?
Yes, Mark.
Hi, thanks for your talk. I guess it should be clear, but maybe you could just say it. The same will be true for Renyi entropies and Renyi relative entropies because of the x to the alpha function.
I think as long as we have these logarithms involved in the definitions of our entropies, we have to be a bit careful. If there are no, if we don't have these usual suspects of the transcendental functions, I think almost things become algebraic or semi-algebraic. But as long as we have these involved, I think we have to be careful because things might get transcendental.
Sorry, like
or maybe
Renyi, where alpha is not an integer. Shouldn't this be transcendental?
When alpha is not an integer.
Yes.
There are, there are numbers which are not integers and are still algebraic numbers.
Oh, okay.
Yeah. So basically, my plan is to continue and study these other well-known entropy measures like this, or the mutual information, and see whether these things hold there also.
Well, I mean, I guess the Renyi entropy, it's 1/1 minus alpha, and it involves log, trace root of the alpha. And so
Yeah.
anyway, I guess you'll discover it in your future plan.
Let's hope.
Thank you.
Sure. I think there was another question. I saw a hand raised somewhere.
Other question or comment?
There's a question in the chat.
Yes. It says this operation shows that there is no one-shot characterization for transcendental case. This basically shows that there is no one-shot characterization for entropy measures, which are defined like this and use a finite ancillary system, basically. Because whatever we are comparing this with catalytic transformations, and those are always, so this set Sn was always semi-algebraic for finite ancilla. But if this ancilla is infinite, then this is no longer algebraic, basically, because this is what our problem is showing. Yes, you can use basically the same argument. But I would say that this separation shows there is no one-shot characterization for algebraic, because entropy level sets are transcendental. Does this answer your question? Okay.
Other question or comment? So maybe, thank you very much. So now we want to proceed to the next talk.